Now we will present our user case. First of all, it will be application 1, inhibitor selection and efficiency prediction. Lisa Sahlmann from Helmholtz-Zentrum Hereon will present this case. Lisa, please start. Floor is yours.
All right, thank you, Natalia. Okay, I hope you can see it now. Yes, I'm a PhD student at the Helmholtz-Zentrum Hereon, and I am presenting our first use case today, the App1, which is about the workflow how to select corrosion inhibitors. I want to start off with a little thought experiment. Imagine that you want to find a suitable organic corrosion inhibitor because you are designing a new coating. If you can run maybe 6 experiments in parallel, which run for 24 hours each, then if you want to test all the organic compounds in the chemical abstract service database, you would need around 68,000 years. And if you even imagine that there are 10 to the power 59 synthesizable compounds, 10 to the power of 63, you would need 10 to the power 59 years. And we wanted to finish the project a little earlier, so we had to come up with a new idea. For a little comparison here, the observable universe has 10 to the power of 21 stars to give you some perspective. So how are we going to tackle this problem? So how can we shortlist promising corrosion inhibitors for prototyping and testing? And that's the point where machine learning for us came into play. So our goal was to identify quantitative relationships between the properties of the molecules and their structure. So in our case, properties means that they are suited for corrosion protection of our metal for the aluminum alloy 2024. And about the structure, I will go into that in a second. What we mean by that, how we quantify that. For a robust machine learning model, it is called a quantitative structure property relationship model, QSPR model. We need, first of all, sufficient and sound training data, which also includes a target property. So in our case, that means we need enough molecules that are tested for their corrosion inhibition properties. Then the second point here is we need input features. Here the structure of the molecules come into play. So the question is how we encode the structure of the molecules to put them into the machine learning model. And the third point is that we need a suitable model framework. This could be an artificial neural network, random forests, many different machine learning models out there. Now I want to go a little bit more into detail in all these different points. So the first one, the database that we need to train the machine learning model. As I already mentioned, we are using the aluminum alloy 2024 T3, and the samples were mechanically sanded and polished, and then the samples were exposed to a water solution containing 0.1 molar of sodium chloride and the respective small organic molecule that we wanted to test. The tests have been conducted at TU Delft, and they were running linear polarization resistance measurements. These measurements have been done every 10 minutes for the first 24 hours. And the pH was measured before and after the experiment. Now about how to encode the structure of the molecule. We are using so-called molecular descriptors. And these descriptors can be anything about the structure of the molecule. So it could be which functional groups the molecule contains. It could be the topological or Euclidean distances in the molecule. It can be density functional theory and so on. And so everything that you somehow can put into a number about the structure of the molecule. We used 2 different softwares, AlphaDesk and RDKit, to generate these molecular descriptors. And here you can see the overview or the workflow that we used. So we start off with building the database. As I mentioned, this was done at TU Delft, and organic molecules have been tested. Then we are generating the molecular descriptors in the next step, and the number of molecular descriptors that we generated was really large. So we could not put them all into the machine learning model because they would degrade the model if we put molecular descriptors in there that might not have a relevance to the model target. And so we had to reduce the number of features, which we have done using a technique called recursive feature elimination, which basically means that we take all the molecular descriptors that we've generated and train the machine learning model, in this case a random forest. And then the random forest has an internal feature ranking, and we could omit the lowest rated feature. And then we repeated this process until we ended up with the desired number of features. So we usually went for 10, 6, or 3 features. And once we had the features that we wanted to put into the machine learning model, we of course trained the model. We tried out different ones, and we ended up with usually using random forests because they gave the best performance. A little bit about random forest, or in general committee learning. So random forest is constructed by a multitude of decision trees. These are the little trees here on the slide, and the decision tree is in a hierarchical structure. And the different branches here, they represent the decision-making steps. And then in the end, every tree is making a prediction, which is combined using the average of the different predictions to give an overall prediction, which is the degree of corrosion in our case. And we are using 2 different metrics. We are using the inhibition efficiency and the inhibition power for prediction. And now we want to look at some results. So we went into this active learning cycle, meaning that we started off with training the random forest on 60 molecules. And then we did different rounds of training, and in every round we added 5 molecules where the previous model was most unsure about in their prediction. And with that, we extended the data set step by step, and until we went to 85 molecules, and a few molecules were held back for blind testing. So the models have never seen these blind test molecules. And here we can see the results for the blind test. We could see that the root mean square error goes down with adding new molecules, and the R squared goes up, which is a good sign. So adding new molecules improves the performance. And we could see the same for the inhibition power as target, and the same trend, although the inhibition power gives a bit worse results than the inhibition efficiency. And that's it from the theory behind the App1 model. And now I want to go into the platform and show you the landing page of App1 and how you can use it. So you can see the platform now. So we are here. I already logged in, and then we can go to the landing page of App1. So the first thing that you can see here are the KPIs, which is the inhibition efficiency. I already talked about this. The second one is the toxicity, and the third one is the price. Then you get a little explanation about how the inhibition efficiency is calculated, and you have some links here. So for the training data set, when you click on this, you can see which molecules have been used for training the machine learning model. So here it goes from the accelerators to the inhibitors. Accelerators are also needed for training so that the model can distinguish between good molecules and not so suited molecules. Okay, going back to the landing page. So now you can put in a molecule that you are interested. Let's try this one. And so you can put in the name of the molecule, or you could also put in the smiles. You can search for this molecule, and then you get some information. You get the CAS number, you get link to reach, you see the structure here, and then we have different things linked here on the landing page. We have the GHS classification, we have information about restrictions, toxic dosages, references, and also the chemical vendors. You can take a look here. Many vendors are listed, and so this is a way to find something about the price. If you click the link, you get to the homepage and you can see how much you would need to pay for this molecule. And then, once you found out about the different KPIs, you can run the machine learning model. So you also get the smiles here of the molecule, and then you can run App1. And here we have the result. So in this case, we get an inhibition efficiency predicted at 67%. And that's basically how you can use App1. Thank you.
Thank you very much, Lisa, for this demonstration and presentation of the results. Thank you.